So this is section 4.9, and we're going to be talking about Newton's method. And I think that there's some nice irony here about the origin of Newton's method and things like this. Isaac Newton, in the 16th century, you've got to compute stuff, right? You're doing all this math, you're getting physics done, and when you go to compute stuff, you don't have calculators. That makes things challenging. So one of the things that they looked for in mathematics at that time was how can I more quickly compute things? How do I solve basic equations that don't have nice number answers? And so this is kind of, getting back to that idea of like, okay, if I'm doing things by hand, how can I get a result, right? For example, we take for granted if I wanted to type in sine of like 41 degrees, I can just type that on my calculator and get a number. And if I need to use that for something, that's no problem. I have those decimal places. And if you didn't have a calculator, then you don't really have a nice way of doing that. You have to come up with some method for approximating. And that's what we're developing here. Now, the reason that I say that this is ironic is because it seems like methods like this have become even more important, because now that we have computing devices like calculators and computers, we need to tell them what to do. And computers and calculators are not any smarter than humans. And in fact, if you go to like the microchip level, computers can really just add and multiply. They can't really do much more. So everything that we want them to do, we need to design an algorithm to tell them to do that. And something like Newton's method, where we can just sit there and do extra computations to get more accuracy, are perfect for something like a computer. So even though this algorithm and ones after it originally designed to enable humans to compute better, it's actually better. Computers are better equipped to do it. It seems like it's better designed for computers than for humans. All right, so let me give you sort of a motivating example. Suppose I want to solve something like x to the fourth minus. Oh, you know what? Let's make this a fifth degree. There are indeed formulas for solving a fourth degree polynomial, but they're terrible. Nobody ever uses them. Let's make a fifth degree polynomial. Let's suppose I have a fifth degree polynomial and I want to solve that. If you have a second degree polynomial, then all of you know the quadratic formula. If you have a third degree polynomial or fourth degree, there are formulas that you could use similar to the quadratic, but they're not very nice, and you kind of have to break it up into special cases depending on what all the coefficients are. For fifth degree and higher, not only is there not a formula, but it's been proven that you can't create a formula that will always solve every fifth degree polynomial equation. And if you have like something that's not a polynomial, right? Like if I'm trying to solve a trig equation, then same problem. We don't have a way of doing that to get exact answers, right? We could say, oh, you can use the inverse sine, but what is inverse sine of 41 degrees, right? Like how do you compute that? What we're going to do is look at a way for approximating solutions. So if I have problems like this, or something like tangent x minus x equals 0, right? That's another easy to write down, but it's really difficult to solve, at least to get to exact answers. We're going to get to answers with numerical approximations. Okay, we talked about numerical approximations a little bit in the last chapter when we looked at linear approximations. Let me just give you a refresher for a linear approximation, and I'm not going to use these more complicated examples yet. I'm just going to draw a graph to begin with. So let's suppose that I have, some function, and I want to find where it's equal to 0. Well, with a linear approximation, what we did is we said, well, if there was a number that I could plug in that was easy to plug into the function, we can create a tangent line at that point. And the tangent line, although that tangent line looks a little bad. Let's try a better one. Okay, the tangent line should be close to the function as long as our x values stay close to a. So if I wanted to approximate where this root was, I could look for where the tangent line hits 0. Okay, so this would be my So that would be my approximation of the root using the tangent line. When we did a linear approximation, we found that the approximations were generally pretty good, like we'd get 1 or 2 decimals of accuracy. And if that's all you need, then that's great. And if the x value is further away, you would be less accurate and out of luck. Or if I had some specific application where I needed 5 or 6 decimals of accuracy, or I'm designing a calculator, I show 8 decimals of accuracy on the screen, I need to have 8 decimals of accuracy, then that linear approximation bit is, it's not going to do it. It's not enough. So what we want to do is look for a way to solve equations where we can improve our accuracy, where we can say, here's my approximation, and now let me do more work to make it better. So that's what we want to do with Newton's method. Okay, so if I'm looking for this root and I find an approximation using the tangent line, what I can say is, well, that's one approximation. Can I get a better one? So what we do is we say, I'm going to use that x value as the next place that I create a tangent line. Okay, so let me, I'll try to draw this in here, although it's going to get cluttered really quickly. But we're going to create another tangent line here. And the x value we pick is the x value that we got from the first tangent line. And then we look for, where does that one hit 0? Okay, and the way I've drawn it, that kind of lands almost directly on the root. Okay, but the idea is that we can keep repeating the process and get closer and closer. So I'm going to draw just one little piece of a graph. So the idea is, let's say that x0 is my initial guess as to what the root of the function is. At x0, I create a tangent line. Okay. And where that tangent line hits 0, where the tangent line has a root, that's my next guess. So I'll call that x1. So that's my first approximation. So then I create a tangent line at x1. And where that tangent line hits, right, has a root, that's my x2. So then, we repeat the process, right, where that tangent line, create a tangent line at that point, where it hits will be my next guess, x3. This is how we can create an iterative process, right? And the way that I've set this up is this is for finding the root. That's different than solving an equation. It is like solving an equation that looks like this, though, right? Where I can say, okay, if I have an equation equal to 0, then that's finding a root. So what we do is, for Newton's method, we're going to set up solving an equation to be having stuff equal to 0, and then thinking of that stuff as a function, and then we want to find the root of that function. Before we get into an example of that, let's look at how I can make this a clean iterative process. I don't want to start from scratch each time I find a number, go through the process of finding the equation of a line, and then go through the process of finding where does that line hit 0. That's too many steps. Let's see if we can condense the number of steps here. Okay, so what I'm going to do is I'm going to say, how do I, in one step, find an equation of a tangent line, and then also find where does that tangent line hit 0. Let's look back here and suppose I'm plugging x0 into my function. Let's say, what is the equation of the tangent line to f of x at x equals x0? Okay, and I know from my linear approximation work that that's going to be L of x equals f of x0 plus f prime of x0 times x minus x0. All right, now the only thing I need out of the equation of the tangent line is where the tangent line hits 0. So now what we're going to do is say, now solve L of x equals 0. So I'm going to have f of x0 plus f prime of x0 times x minus x0 equals 0, and I want to solve for x. Okay, So we're going to start by subtracting f of x0 from both sides. So we have f prime of x0 times x minus x0 equals negative f of x0. Then I'm going to divide by this f prime. I have to be careful. If f prime of x0 is 0, this will be a problem. Okay, and we'll discuss that in a minute when we look at the problems that Newton's method can have. So now we have x minus x0 equals negative f of x0 over f prime of x0. And then our last step is going to be add x0 to both sides. So then we have x equals x0 minus f of x0 over f prime of x0. Okay. This gives us the value of our next guess. So our first approximation, x1, is going to be x0 minus f of x0 divided by f prime of x0. Then if I want to find my second approximation, x2, I'll just repeat this process, except instead of using x0, I'll be using x1s. Okay. So my second approximation, x2, is going to be x1 minus f of x1 over f prime of x1. All right, well then that gives me an iterative process, right? So let's go ahead and write this down. So here's what Newton's method is. Solutions, or I should say, we'll say solution to f of x equals 0 using x0 as an initial guess, okay, can be approximated by. So I'm going to say xn, the nth approximation, is we take the previous approximation minus f with that previous approximation plugged in, divided by f prime with that previous approximation plugged in. Okay, so what I want to do is walk through an example using this, and then we'll look at this on our graph and then look how we can apply this in different situations. Okay, so our first example, I'm going to start with something very, very easy. Let's suppose that f of x equals, let's use this crazy polynomial that we started with. X to the fifth minus 6x to the fourth plus 2x cubed minus 7x squared minus 4x plus 10. We want to solve f of x equals 0. Now, there might be more than one solution to this, but Newton's method will give us a solution. What we have to do is start with an initial guess. What do you think will work? You know, I don't really know. Like, we don't have necessarily a nice way to just say, this is what your first guess should be. Let's see what happens if I plug in 1. So let's just say my initial guess is 1. Okay, in order to set up Newton's method, I need to have an f prime. So this is 5x to the fourth minus 24x cubed plus 6x squared minus 14x minus 4. Okay, so then my formula for Newton's method, I'm just plugging in this, f of x with xn minus 1 plugged in, a big fraction bar here. So I'm going to have xn minus 1 to the fifth minus 6xn minus 1 to the fourth plus 2xn minus 1 cubed minus 7xn minus 1 squared minus 4xn minus 1 and plus 10. And then divided by the same thing except with f prime. Okay, so this is kind of complicated when I plug in 1, right? So if I want to plug in x1, then 1 minus 1 is 0. So that's just the number 1. So I'm just plugging 1 in for all of these xn minus 1s, right? Because they're all I want my first approximation, these are all x zeros, and x zero is equal to 1. Power here. Okay, now I'm going to be careful with my arithmetic because arithmetic can be tricky, right? But 1 to any power is just 1. So I have 1 minus 6 plus 2 minus 7 minus 4 plus 10, which gives me a negative 4. And then we have 5 minus 24 plus 6 minus 14 minus 4. I get negative 31. A negative over a negative is positive. So I have 1 minus 4 31s. So if I leave that as a fraction, 31 over 31 minus 4 over 31 will give me 27 over 31. So that gives me my first approximation for what this root is. I can leave that as a fraction, or if you want to, write it out as a decimal, I get something like this. In order to plug in with this fraction, this is going to get a little bit complicated, so I'm going to cheat a little bit and use my calculator. So let me just show you how I would go about doing that. Okay, what I'm going to do is under y equals, I'm going to go ahead and plug in my Newton's method. So my Newton's method formula was, for my next guess, take my current guess minus, and then my current guess plugged into the function over f prime. So what I'm going to do is x minus that big fraction, right? So then I'll go ahead and put in the numerator. Let's see if I can get these both on the screen at the same time. Okay, so I have x to the 5th minus 6x to the 4th plus 2x to the 3rd minus 7x squared minus 4x plus 10. That was our numerator. And then divided by, and then in the denominator, we have 5x to the 4th minus 24x cubed plus 6x squared minus 14x minus 4. Okay, so what I want to do is I want to take that thing that I have and plug in my initial guess of 1. So variables, y variables, function y1, and I plug in 1. And I get that number, and that's what we computed. Okay, and now what I want to do is I want to use that output as my next input. And I get another approximation. And then I can do it again, right? So this is my x2, 0.8537. Okay, then we can do it again to find a third approximation. I should enter my calculators, plugging my previous output in as my new input. So I get 0.853467. 4351. And then let's try it again. And here, it's only the last 4 digits that changed. And now if I do it again, I get the exact same number again. What that tells me is that at least up to the 10 digits that my calculator is outputting, that's what the root is, up to 10 digits of accuracy. Now, it's probably not exactly this number, right? For example, square root of 2, you can't write with just 10 digits, but you can write the first 10 digits of square root of 2, right? So same thing here. I'm not saying that this is the exact root. I'm saying that up to 10 digits of accuracy, that's what the root is. Okay. Now, let's go ahead and look at a graph of that terrible polynomial. Not the Newton's method, just like the polynomial as a whole. X to the 5th minus 6x to the 4th plus 2x cubed minus 7x squared minus 4x plus 10. Okay, now I don't want the graph of this first one, so I'm going to turn that off. Okay, I can look at my graph of the polynomial. Maybe we'll zoom out for a second. And I can see, okay, you know, it's 5th degree, but it looks kind of like a cubic here. Right? It goes up, down, up. And so it has 3 roots. And what we did is we found one of them. Okay, so what we found was this one here in between 0 and 1. And maybe just to double check, if I have my calculator compute a 0, when you have your calculator compute a 0, it first asks for a left bound, and then a right bound, and then give us a guess. I think it's about here. And then it computes it. It's actually doing an almost identical process to what we just did in order to find a root, right? You start with those bounds and give an initial guess, and then it'll do an iterative process until it gives you all the decimals of accuracy that it has, right? 0.853. Okay, so you can see, all right, we have a nice method for approximating here. And it actually worked pretty fast, right? When I started with an initial guess of 1, that turned out to be pretty close, but I was just guessing something easy to plug in. And after 1 guess, we were at 1 decimal of accuracy. After 2 guesses, we were at 3 decimals of accuracy. After 4 guesses, we were at 6 decimals of accuracy. And after 3 guesses, we're at 4 decimals, and after 4 guesses, we're at 10 decimals of accuracy, right? So we're adding like multiple decimals of accuracy with every single computation. That's pretty good. You know, a computer can do one of these steps like almost instantly, right? All right. Let's look at another example that doesn't look like the same type of setup. Approximate the square root of 2 using Newton's method, right? That sounds like what we want to do. We want to be able to say, take something that's hard to compute and approximate it, right? So this sort of fits the bill, but it's not really set up right. Newton's method, I need a function. There's no function here. So what we need to do is create one, right? We need to create an equation and a function and so on. What I'm going to do is I'm going to start by saying the thing I want to find, I'm going to call it x. So let x equal the square root of 2. And what I want to do is get a function equal to 0. I want to have numbers that I can plug in nicely. And if my assumption is that I can't find the square root of 2, then it doesn't make sense to cheat and use square root of 2 on my calculator. Okay, so what I'm going to do is I'm going to square both sides and then subtract to get equal to 0. Okay, so if I can find the roots to x squared minus 2, then one of those will be the positive square root of 2. And so approximating that will give me an approximation for root 2. So this is what we want to solve. So we're going to let f of x equal x squared minus 2. So f prime of x is just 2x. Okay, that means that my Newton's method formula is going to look like x. You know, earlier I wrote this as xn plus, or xn and then xn minus 1s. I'm going to write xn plus 1. The next guess is going to equal the previous guess minus f of the previous guess divided by f prime of that previous guess. And my function is just x squared minus 2, and the derivative is just 2x. So all we need is a first approximation, right? We need an initial guess. Well, you know, I know the square root of 2 is between 1 and 2. Let's just go ahead and pick an initial guess of 2. So then my next guess is going to be 2 minus 2 squared minus 2 over 2 times 2. So 4 minus 2 is 2. So I have 2 minus a half, which gives me 3/2. So then our second approximation is going to be 3/2 minus 3/2 squared minus 2 over 2 times 3/2. And this one I think I can compute by hand too. The next one is going to get to be a little bit rough, but this one let's try out. When I square 3/2, I'll have 9/4. And 2 times 3/2 is just 3. 9/4 minus 2, this is 9/4 minus 8/4 over 3. 9/4 minus 8/4 is 1/4. Divided by 3 is like times 1/3. So I have 3/2 minus 1/12, which is, if I get a common denominator, multiply by 6. So I have 18/12 minus 1/12 is 17/12. Okay, so that's my next guess, x2. Beyond that, I'm going to have to cheat and use my calculator. Okay, so our formula was x minus x squared minus 2 divided by 2x. So when I plug in my y1 function, we started with 2, and we got 3/2, which is 1.5. And if I say plug in my previous answer as my new input, my next one is 1.416 repeating. Okay, and then we get a few more guesses. So the 1.5 was our x1. Our x2 was 1.416 repeating, which is 17/12. So our x3 is 1.414215686. x4 is 1.414213562. And since the next guess is the same thing, we're not getting any more decimals of accuracy. We're done with new decimals of accuracy. Okay, and maybe just for reference, if I type square root of 2 into my calculator, right, I get the exact same thing. Okay, so this is how we can use Newton's method to find the value of a difficult constant to compute, right? And we're not computing it exactly, we're getting an approximation, a decimal approximation. All right, let's look at some problems that Newton's method can have. I want to illustrate these by looking at graphs because I think it's a little bit easier to understand. Okay, so let's suppose that I have some function and I want to find the root to that function. And let's suppose that at my initial guess just happens to land exactly on a horizontal tangent line. This line never hits the x-axis, so I don't get a next guess. I don't get an approximation. What we can see going on there is that in my formula, if one of my approximations hits a horizontal tangent line, I get a divide by 0 in my Newton's method. And so it breaks down, right? So whether it's my first approximation, right, my initial one, or whether it's any of the ones in the process, if they exactly hit a horizontal tangent line, then the whole process just breaks down. If I don't hit a horizontal tangent line, but I hit a point maybe close by to one of them, right, maybe my initial guess was like over here, okay, then that's going to send me kind of far away. Oh, I'm actually coming close to a horizontal tangent line again. Let me back that up. Oh, let's actually go a little bit closer. Let's suppose I hit like this point. Okay. Then my next guess is going to be here. And then my next guess is going to be here. Okay. And we end up finding the wrong root. Okay. So just because my first guess was close to one root doesn't mean that that's the one that Newton's method will take me to. It might take me to a different one. Okay. Newton's method completely fails if we hit a horizontal tangent line, but in general, if I hit a point of the graph where the tangent line just has a very weak slope, I'm going to travel far away from that guess to get my next one, and that's where weird things can happen. So I can end up hitting a different root than the one that I thought. There's also a you know, again, this is a contrived example, but this is a possibility when we talk about Newton's method. Let's suppose that we have this function. So let's suppose f of x is x cubed minus 2x plus 2. Let's find the roots of f of x equals 0 using Newton's method. And let's just say, you know, pick maybe 1 for your initial guess. Okay, so f prime of x is 3x squared minus 2. So then my formula is xn minus f of xn over f prime of xn. I'm just going to, yeah, here's my derivative, 3xn squared minus 2. Okay, I'm going to just do all of these on my calculator because I just want to demonstrate this really quickly. So we had x cubed minus 2x plus 2 divided by the derivative, right, 3x squared minus 2. Oh, and actually, I probably could have computed this out by hand. But when we plug in 1, I get 0. When I plug in 0, I get 1. So it's just going to bounce back and forth between the two. Okay? So if I look at a graph of what's going on, right, I have my function. So here's 0, here's 1. And when I plug in 0, the tangent line hits 1. When I plug in 1, I didn't draw my graph very perfectly, but no, yeah. So I didn't draw my graph really well, but the tangent line at 1 hits 0. So it just bounces back and forth. And the difficulty that it has is that the function dips down like it has a root, but there's no root there. It curves back up again. And so that creates a problem for Newton's method. It can get stuck in this dip and just bounce around. So Newton's method may fail if the function gets close to having a root but turns around. I'll call that a false root. There can definitely be some problems with Newton's method. Okay, if you want to study iterative processes and you want to look for ways to find roots, we actually had a method for finding roots that sort of comes up, that we didn't fully explore, but comes up way back when we talked about the intermediate value theorem. Okay, so this isn't Newton's method, but I'm gonna show you another process that we can use to find roots of functions, just using the intermediate value theorem. Okay, so this is called the bisection method. Okay, and here's how it works. Let's suppose we have a function, and I'm going to use that nice root 2 one because it's very simple. So like the x squared minus 2 equals 0, right? So f of x is x squared minus 2. The way that this one works is I need to find, if I'm looking for a 0 of a function, I need to find a value that's negative and a value that's positive. Okay, those are going to be my initial 2 guesses, right? So x0, if I plug in 0, I'll get a negative. And then maybe I'll plug in, like, for my other guess, I'll plug in an x value of 2, and that'll give me a positive. Okay, so we have 1 negative, we have 1 positive. That means that somewhere in between is a root, and according to the intermediate value theorem. And so what we do is we pick halfway in between. So if I average 0 and 2, I'll get 1. So what I do is I plug 1 into the function and see what happens. I have 1 squared minus 2, which is negative 1. Because that's a negative, that replaces my old negative, right? So I still have a negative and positive, but now my negative and positive come from 1 and 2. So I average those two together to get 1.5. Okay, now I don't want to square decimals in my head. So when I plug in 1.5, I'll get 0.25. That's a positive, so it replaces my other positive. So now I know that the root is in between, right? My positive is at 1.5, my negative is at 1. So it's halfway between 1 and 1.5. So when I add those together and divide by 2, right, when I average them, I get 1.25. So then I test 1.25. Okay, and I get a new negative, 0.4375. That's a negative, so now I know that the actual value is halfway between, or is in between 1.25 and 1.5. So I average those together, and I get 1.375. Okay, and I plug that into my function. Okay, and we get a negative. So that replaces this negative, so now I'm in between 1.5 and 1.375. So I take 1.5 and 1.375, and I average them. And I get 1.4375. Okay, and now I want to plug that into my function. Okay, and we get a positive. So now I know that the root is in between 1.375 and 1.4375, and this is getting somewhere. I'm just trying to get down to 1 decimal of accuracy. And I get 1.40625. And when I plug that into my function, I get a negative. So I know that it's somewhere in between 1.4375 and 1.40625. So far that means that I have 1 decimal of accuracy, because it's definitely going to be 1.4 and then something. So we get 1 decimal so far for the square root of 2. And what happens with this method is that every single step that I do, I'm going to cut my interval in half. To get a decimal of accuracy, I have to cut my interval by 1/10. Well, if I cut in half 3 times, that's 1/8. So it takes a little bit more than 3 steps to get a decimal place of accuracy, right? So I got my first, got my first decimal place of accuracy, right? 1. That's the ones place. And then, I've got to do a little bit over 3 steps to get my next decimal of accuracy, right? And so on. So it's pretty slow. If I compare that to Newton's method when we were doing the exact same thing, right, for the square root of 2, we were getting 3 decimals of accuracy at every 1 step, right? Instead of 1 decimal of accuracy at every 4 steps. So this method is a lot slower, but it's not as sensitive to my initial conditions. As long as I start with a negative and a positive, it will home in on a root. It doesn't matter if there are horizontal tangent lines or anything like that. And so one of the things that more modern computing does is that instead of looking at just one method for computing roots, you might take a combination of methods, right? So we might start off with something like this that's not sensitive to initial conditions and try to get close to the root. And once we get close to the root, you might switch over to something like Newton's method to get decimals of accuracy really quickly. And so you use a combination, and that way you can maximize your computing power while also not subjecting yourself to some limitations. Now, Newton's method is over 300 years old, so there's been a lot of tweaks and add-ons over the years, right? When you look at a computer, it's not quite just this. But this gives you an idea, right? By looking at 2 methods and seeing how we can combine them, you can start to get, I think, a sense for how numeric computing actually works. And that's really what we want to do here. We just want to get a sense for numeric computing. All right, I think that's it for Newton's method.